Hello, Math 201. Welcome to section 4.1, maxima and minima. So we will start chapter 4, applications of derivatives, and really just continue on this path that we started in last lecture. And today we're going to look, and actually for quite a while, we're going to look at this kind of very important fundamental question, which is where is a function largest and smallest? So any sort of function that we care about, what the quantity are, knowing where its largest and smallest is a really fundamental, very important thing to know about a function. And these things are called maxes and mins. And so a couple definitions. We're going to use the term absolute. Maybe some of you heard global, but we're going to use the term absolute max and min to mean the absolute largest or smallest a function is on a given interval. By definition, the absolute max is the largest value that a function gets on a domain or a set, and an absolute min is the smallest. And if we just want to be generic, we'll say absolute extreme value. So that means either absolute max or absolute min. It's easy to see kind of what we mean by a picture. So this is an absolute max because on its entire domain, there's no number bigger. And then this one is, if we just restricted our domain to just 0 to 2, then this is still an absolute max. And now this is an absolute min, whereas this one doesn't have an absolute min because these guys just keep going off to negative infinity. If we restrict our domain even further and don't include this point, then this one actually doesn't have an absolute max. You could say, oh, maybe it's like a point really, really close to there. But the problem is the closer and closer you get to x equals 0, the closer and closer we get to 4, right? The limit is 4, but there actually is no largest value because you could get arbitrarily close. But it does have an absolute min. And if we got rid of the endpoints, then there's actually no absolute max or absolute min. And so what our domain is for our function is very important when we talk about absolute maxes and mins. If we have the entire domain, there was an absolute max, but no min. If we have a closed interval, there's always an absolute max and an absolute min. If we have a kind of mixed interval or an open interval, there's no guarantee of an absolute max or an absolute min. So, and a closed interval, though, isn't enough to guarantee a global max or a min. For instance, here's an example of a closed interval where there is no absolute max because this is the piecewise function that's that. But then if you plug in 0 or if you plug in 1, you get 0. And so it wants to go to this value, but the actual value is there. And so there is no max. Similar for this one, we kind of have this piecewise function and it wants, that's really the highest value, but it doesn't actually exist, even though it's defined on a closed interval. And so in order for it to have an absolute max, it needs to be a closed interval and continuous. And this is a very important theorem. It's called the extreme value theorem, which we won't prove, but the picture is basically this. If this was continuous and it's closed, then there's going to be an absolute max. And so if a function is continuous on a closed interval, it has an absolute value and an absolute min. And so let's look at an example on how to find them. And so here is a function. Identify the location of the absolute max and absolute min. And then if it doesn't, why does it not meet the extreme value theorem? So this one's pretty easy to do. It's a nice continuous function. It's even differentiable. There's no like hard points on it. The absolute max, this is the highest value. There is no value higher than that. And so x equals a is our absolute max. And then as we go along here, this value down here is the absolute min because there's no value smaller than it. Over here, this one has an absolute max, but no absolute min because it's not on a closed interval and it's not continuous. And so it does not meet the criterion of the extreme value theorem. So, but it did have a max, but no min. Now we're going to shift gears. So absolute max and min hopefully is pretty straightforward. Now let's shift gears and talk about local max and min. So a local max and min, and again, this is easiest to do by a picture. So a local max and min is a point where everyone around them is either bigger or smaller. And so it's like the bottom of a valley or the top of a hill. Those are local maxes and mins. The reason why we call them local is because even though he's the smallest guy around him, he's the bottom of his valley, there could be someone smaller, or there could be someone even smaller. So for instance, this guy's even smaller down here. We also note that endpoints can never be local maxes and mins. When we talk about local maxes and mins, we really just mean in the middle of a function. And then this right here is a local max, but he's also the global max. There's no value bigger. This one is a local min, but not the absolute min, because that's the smallest. This one is a local max. Whoops. So even though it's not smooth like this, it is bigger than everyone around him. So he's a local max. And this one is a local min because he's smaller than everyone around, even though this one's even smaller. So that's the idea. And here's the definition. I won't bore you with it, but the idea is that if it's greater than or equal to everyone around, it's a local max. If he's smaller than or equal to everyone around, then he's a local min. So f of c is smaller or bigger than all nearby x. So it's top of a hill or bottom of a valley, or it could be sharp. They could be sharp, things like that. So I really should add, it could look something like that or something like that. It doesn't have to be differentiable. So find all local extrema. So here's an example. So where are all the local extrema? Our candidates are going to be right here, right here, right here, and right here, right? The top of the valleys, or the top of the hills and the bottom of the valleys. And so x equals p and r, those are local min. Local mins, I guess, I don't know. And then x equals q and s are local maxes. And so that's pretty straightforward, not too bad. So local min, max and min, pictorially or graphically is really easy. What we're going to kind of spend a little bit of time doing is how do we find it analytically or through the actual algebra of it. Okay. Another thing to know about local maxima and minima is that something happens with the secant lines. As we approach it from the right, these secant lines are getting flatter and flatter until the secant line becomes a tangent line and it's flat. And as we approach it from the right, the secant lines are getting smaller and smaller. And so it seems like there's something about what the tangent line is here. And remember what the slope of the tangent line is. The slope of the tangent line is the derivative. So there's something going on with the derivative at a local max or min, given that it exists, right? Because you could have this situation where it's a hard point and a hard point and it doesn't exist. And so if the derivative exists at a local max or min, it's actually going to have to be zero. And this is what's called the local extreme value theorem. If f has a local max or min value at c and the derivative exists, then the derivative has to be zero. And so this local extreme value theorem is very, very helpful, and it gives us a criterion on how to find local maxes and mins. So for instance, here's one that's a local max, but the derivative does not exist, so it does not meet the criterion. Here is another one where the derivative is zero, but that's not a local max or min. So this is a function, f prime of x equals 3x squared. If y equals just x cubed graph. The derivative is zero at zero, but that is not a local max or min. So you need both. So it's one way. If it's a local max or min and the derivative exists, then the derivative is zero, not the other way. This implication is false. You cannot go backwards. Also, you could have something like this, where f prime of 0 is infinity. So you could have the derivative doesn't exist at 0. And it's neither a local max or local min. And so that's another way where you could get that. And so candidates, so these guys where the derivative is 0, this is possibly where you can have a local max or min, or you can have a local max or min where the derivative is not defined, so something like that. And so those candidates are called critical points. And so the definition of a critical point, an interior point C of a domain for which the derivative is 0 or the derivative doesn't exist is called a critical point. These are critical points because these are the points where the function could have an absolute max or min. And so here's an example of finding critical points. And so all you do is you set the derivative. First thing you need to know is what the domain of a function is. So if our function is x squared times ln of x squared, you can plug in anything. Ln of x, you have to plug in positive numbers because ln of 0 doesn't exist. It's negative infinity. And so our domain are all positive numbers. And so now, in order to find the critical points, what we do is take derivative, set equal to 0, and solve for x. That's how we find the critical points. So f prime of x, what is the derivative of this function? Well, it's the product rule, so it's 2x times ln of x plus x squared times the derivative of ln of x, which is 1 over x. And so this is 2x ln x plus x, which we could call that x times 2 ln x plus 1. All right, and so set that equal to 0. So f prime of x equals 0. So set it equal to 0. So set equal to 0. So f prime of x is x times 2 ln x plus 1. Set that equal to 0. So x equals 0 or 2 ln x plus 1 equals 0. This one can't work because it's not in the domain. So not in domain. How about this one? What do we get here? We get that ln of x is equal to -1/2. And so how do we solve? We get that x is equal to e to the -1/2, right? That's how we undo. You undo that by doing that. And so x equals e to the -1/2, which is in the domain. So this is critical point. And so right now we know that that is a possibility for where it could be an absolute max or min. All we know is that the derivative is 0 here. We also technically should check to see if there's any places where the derivative doesn't exist in our domain, but because this is our derivative function, it has the same domain as our original function, so there's no critical values where the derivative doesn't exist. But this one is a critical point because this is where the derivative is 0. So x equals e to the -1/2 is a critical point. And so here's a picture of that. Another way to write this, by the way. So e to the -1/2, that's the same thing as 1 over the square root of e, by the way. Same thing, right? And so they have the picture here. So here's our function. It looks like this. And then there's a local min and absolute minimum at 1 over square root of e, comma, -1 over 2e. If you plug this value in right here, you get that value. And so it's a local and absolute min because the tangent line is 0 or has slope 0, and then it actually happens to be the absolute min because the function is always getting bigger to the left and to the right of it. Okay, so that's an example of finding critical points. Now we're going to use this fact of critical points, and it actually allows us to find all absolute extrema on a closed interval. And so this is a procedure that we're going to use, and a lot of your homework problems will be like this. So locating absolute extreme values on a closed interval. So you need two very important things. The function has to be continuous on the closed interval. Very, very important. And this is what you're going to do. First thing you do is locate the critical points inside the interval. So we don't check the endpoints. We just check for critical points inside. And you want to find where the derivative is 0 or the derivative does not exist inside this interval. It has to be inside the interval. Then what you do is you're going to make a table, and you're going to evaluate at the critical points and the endpoints. And I'll show you what that looks like. And then you're going to have a list of function values, and you just choose the largest and smallest. The largest one is the absolute max, and the smallest one is the absolute min. And so that's pretty much it. And so let's do an example. So it's really kind of just 2 steps. Step 1, find the critical points. Step 2, plug them in and the endpoints into a table, and then you look at your table. And so let's do that. So step 1, find the critical points. So what is the derivative? The derivative of this function is just 4x cubed minus 6x squared. Set it equal to 0. Because it's never, right, this function's never undefined, right? You can plug in any value, so we're just going to set it equals 0. And what do we get? You get that x squared, maybe 2x squared is 2x minus 3 equals 0. So x equals 0 or x equals, what is it, 3/2? X equals 0, 3/2. Those are both in our interval, so those check out. So step 2, make the table. Make the table. So how are we going to make a table? Ooh, boop. We're going to make a little table like this. On the left-hand side are the x values. On the right-hand side are going to be the function values, f of x values. the x values that you put on this table are the endpoints of our interval, so -2. You're going to put all the critical points, so 0, 1.5, and then the other endpoint 2. So those are going to be all the values we check. And you plug them in, you plug these guys in to the function. And so let's remind ourselves what the function is. Copy, paste. So we were going to plug them into there. And so plugging it in, I get -2 to the fourth minus -2 times -2 to the third. What will that give us? -2 to the fourth minus -2 to the fourth. So this is going to be 0. That one's going to be 0. If we plug in 0, we also get 0. If you plug in 1.5, I'm not really sure what that is, but it will be 1.5 to the fourth power minus 2 times 1.5 to the third power. This is going to be some negative number. You can plug into your calculator, but I'm not entirely sure what it is. And then if you plug in 2, what happens if you plug in 2? You're going to get, let's see, it will be 2 to the fourth. Oh, you know what? Actually, this one should have been actually not 0. I messed up here because this is -2 to the third minus 2. And so this is actually going to be plus. It will be 16 plus 16. 16 plus 16. So this is 32. And then if you plug in 2, this one's actually going to give you 0 because it will be 2 to the fourth minus 2 times 2 to the third, which is 0. That's the one that's also 0. And so this one is going to be our absolute max. So the point -2, 32 is the absolute max. And so what you could do is you could just circle it. So that is our max. And then this one is going to be our min because I know that this number is negative because 1.5 times 1.5 cubed is going to be smaller than 2 times 1.5 cubed. And so I know that number is less than 0. I don't know what it is exactly, but it's less than 0. And then 1.5 comma, I guess I can pull out 1.5 cubed. I'll just leave it. So 1.5 to the fourth minus 2 times 1.5 cubed, which I know is negative, is absolute min. Absolute min. And so this is the min. So the max happened at an endpoint and the min happened at a relative minimum. And so that's how we use this procedure. So you don't even have to calculate or any derivative values. You just you solve for when the derivative is 0 or undefined, and then you make a table with the endpoints and those critical points, and then you just see what the function values are. All right, let's do one final example. So again, step 1, set the derivative equal to 0. So we got to find the derivative. What is the derivative? This is going to be a product rule. So the derivative of x to the 2/3 is going to be 2/3 x to the -1/3, and then times 2 minus x, and then plus, leave that guy alone, and then times the derivative of this guy, which is just -1. And so we probably want to simplify this a little bit. So this is going to be, how would I want to simplify this? Well, let's just set it equal to 0 and solve. So set this equal to 0 and solve. Let me rewrite it. So it's going to be 2/3. Maybe I'm going to bring that x to the -1/3 on the bottom. So it's 2 times 2 minus x all over 3 times x to the 1/3 power plus, or minus, sorry, minus x to the 2/3 power equals 0. When I look at it like this, it's clear that if I plug in x equals 0, that this will be undefined. So g prime of 0 is undefined. right? That's clear because if you plug in 0, you're going to divide by 0. That's problematic. So that's going to be a critical value. So x equals 0 is crit value. The other thing is we can solve for this. And the way we're going to solve for this is you get 2. So kind of bring that over here. You get 2 times 2 minus x all over 3 times x to the 1/3. And then just add x to the 2/3 to the other side. And now we can multiply, and you get 2 times 2 minus x equals 3. And then x to the 1/3 times x to the 2/3 is just x. Now we can do this. 4 minus 2x equals 3x. And so you get x equals 4/5. So x equals 4/5 is a crit value, And both of those values, x equals 4/5 and x equals 0, are in our interval -1, 2. So let's make our table. So make the table. Make the table. And so what do we got? So x and then g of x. What is g of x again? It's this guy. All right, so what are the x values we're going to plug in? We're going to plug in -1, 0, 4/5, and 2, because those are our endpoints. 0, 4/5, and 2, right? That guy and that guy are endpoints, and those are our critical values. Now we plug them in. If you plug in -1 to the 2/3 power, that would be 1. So -1 to the 2/3 power is just 1. And then times 2 minus -1. So that will be 3. If you plug in 0, you get 0. If you plug in 4/5, let's not do that one yet. If you plug in 2, you get 0. So that's 0. If you plug in 4/5 to the 2/3 power, and then times 2 plus 4, or 2 minus 4/5. I'd have to plug that into a calculator to know exactly what that is. Let's see what that roughly is. That is roughly, because I'm just curious. I know you won't have a calculator on the exam, and so for exam, I would make the values something that you'd actually know what they are, but I'm just curious. So 0.8, if I take the cube root and then square it, it's 0.86, and then times 1.2. So it's roughly 1.03. And so it appears that this is our absolute max, and that these guys are going to be our absolute mins. So here's our max. So that's our max. And then the two guys at 0. Those are both our absolute min. You can have multiple absolute mins. Maybe I should say absolute. So absolute max and absolute min. All right. And so this critical value at 4/5 didn't actually end up being an absolute max or min. And the endpoints were both important. So that's it. So that should be able to get you through the homework. All right. Take care.